Let's just wait a little bit more for your friends to come and we will start our lecture. Just a heads up, today we are going to just quickly go through the lecture again. We will finish the lab, basically all the labs, right? So we will finish the YOLO v4, YOLO v5, and FASTER/MASC RCNN. And after that, we will have a, what is it called? Like homework presentation. So this one is going to be a 3 weeks homework, and it will count for the last two homeworks, basically. So this will be your last homework, and it will be the biggest. It will have 10% of your final grade, so it will need some time for presentation. And the last part of the lecture will be about, or will be like just quick meetings with individual students, where we just discuss your ideas, discuss your progress so far. I know the majority of you have already started working on some research. So we will just privately discuss you guys one by one. And if you would like just to, so we would have a fair order, please just send me a message telling me you would like to do a one-on-one project presentation, right? Progress presentation. This way I wouldn't have to make the order on the go. Can you speak again? I didn't hear you.
In Telegram, the message?
Yeah, in Telegram, yes.
You are muted.
let's just do this. Maybe it'll work better. Can you guys hear me?
Yeah.
Yeah, we
Nice.
can.
Okay, good. So it took me so much time to configure, what is it called? Zoom on the phone and add a background. So I guess we're going to do it on the iPad again. So as I said before we started, we're going to have a quick recap of the lecture, and then we will finish basically the YOLO v4 lab and the YOLO v5 and FASTER/MASCAR CNN labs. Basically, we just go through the code, explain everything. And this is very important because in your next homework, you're going to be implementing, or you're going to be training each one of these architectures and writing a report about that. We will have more on this discussion basically after we finish the labs and the lectures. We will also read the research paper of YOLO v4, and we try to read research articles that are written about YOLO v5. And today you guys will just, some of you at least, will choose what are the topics you would like to present for next week, right? So remember, as we said, there will be like 5-minute presentations for each student in the end of the lecture, where you just show us some research paper or show us some article that you read, or maybe a new method for doing machine learning in industry or something like that. You just present something that you find is useful and related to either computer vision or deep learning in general. Yeah, and basically, as we discussed, so the end of this week's lectures will be about just some individual discussions about your project and your progress so far. If you haven't started, then it will be just idea discussions, right? Let me share the screen and we start our lecture revision. Do you guys have any questions about the?
Yeah, like regarding those presentations of next week, they will be counted as what, as for an homework, or?
Yeah, it will be just 5% of your grade, right? Presentations, idea presentations.
Oh, okay, because I haven't seen it in the grading criteria.
Yeah, we discussed it. I haven't really set up the grading like criteria so far. So we're just like introducing different things. And for the midterms and for the final exam, what I'm planning to do is basically a what is it called? A written/oral exam, right? So written part will be just a quiz on Moodle, very simple one. And then individually, each student will just come to the discussion, and we will have different questions, and the student will answer, and I will give a grade. Does that work for you guys, or do you prefer maybe written exams, or what do you guys prefer?
No, not written, please.
Yeah, I really like this this way because like last course, some students said that they didn't really enjoy the written exams alone, mainly because the questions were maybe open-ended. So there are different ways to answer, and this is why oral exam is pretty useful. So you can defend your answer basically, right? So you have the open discussion. If I don't find the answer very correct, I will have to ask you further questions, and we will clarify if you understood or not the topic. So this is very useful. And for the quiz part, that's just like, I don't know, just to, I wouldn't say give you guys the ability to cheat, but just give you the ability to see a wide range of competences, right? So in the oral exam, we're just going to take one topic and speak about it, whereas in the quiz, it's just going to be everything that we have discussed, right? Does that work?
Is midterm written or oral?
Both, right? So
Both oral.
yes. So
Okay.
there will be the first part, just a quiz on Moodle, very easy one, just like multiple QCM, like just what is it called? You have just like our quizzes, right? Either true or false or multiple answers. And for the oral part, as we said, person by person, student by student, we're going to go through the course or through some part of the lecture. I will give you the slides. I will give you access to internet, so there is no problem with that. If you would like to see something or maybe have some lecture notes with you, there is no problem with that. And we just discuss what is happening in those slides. Okay?
Yeah, okay, thanks.
Thank you.
So when is the midterm?
Yeah, this is an even better question. So next week, we're not going to have any lecture because I will be traveling. After that, we're going to have the midterm, right? So the midterm is going to be around 27th. And we will have to find a replacement for next week's lectures. For that, what I was thinking is basically adding a 1 hour and a half lecture in the middle of the week. So basically that would replace the 1 hour and a half discussions in the end of this lectures, where I will be able to track your progress twice per week, right? So this will be the way to replace the next week's lectures. And that would give you also some time to work on the homework, because the homework will be super time consuming, and it will give you time to work on your projects. So next week, there is nothing. Next week, there will be your midterm.
And when are the presentations?
What do you mean presentations?
Like the 5-minute presentation you're talking about?
At the end of the next week's lecture.
Okay.
Yes. So at the end of it, always the students will take 5 minutes. You can take up to 15 minutes if you really like the topic and you want to speak about it, but preferably just something in 5 minutes, and you just discuss it, present it to us, and we ask some questions, and that's it. Nice. I hope that you guys still remember a little bit our last lecture. So as you can see in here, we spoke about object detection in general, and we proposed an initial way of doing object detection and using that sliding classifier. And we saw that the sliding classifier idea is pretty much still being used till now, right? So it's not sliding over the original image. So we're sliding over the, what is it called? The latent space extracted from that original image. But our idea or our intuition was very correct, right? So this idea of, sorry, let's just skip all of this part. So this idea of sliding something on the image to find potential locations of objects of interest is still being used currently. So we spoke about how to improve this using this pyramid trick. The pyramid trick is not used like this anymore, but it is still being used in in different models. So we will speak about that also in the lab. And we spoke about selective search, which is something that is completely useless right now because it was removed from all object detection models, I think in 2017 or something like that. So it's pretty old, but it did the job back then. Did a good job. We spoke about intersection over union as a metric for evaluation. And in today's lab, we will speak about mean average precision as another metric for evaluating object detection models. And I'm sure for those who have seen the lab, by default, the metric used by YOLO before and by Mask RCNN and Faster RCNN is mean average precision. We spoke about non-maximum suppression algorithm, and this is something that is still being currently used in all types of object detection models. And the algorithm basically tries to, well, the problem instead, let's start with the problem. So the problem is most algorithms, when they are sliding through the image, you might find, remember, those anchors might overlap with an object. So you will have multiple detections of the same object. So what we do instead is to try and find the prediction for the same object that has the highest confidence score, and all the others, we will eliminate them. Keep in mind, as we said, this is something that is very difficult to work with because there are different scenarios. There are the cases like this where you have just one object inside the image, so that's very easy. But there are cases where you have thousands of objects inside the same image, not thousands, but lots of objects in the same image, and they might be very overlapping, right? So for example, if you are trying to find, what are they called?
to detect human beings that are entering the store or exiting the store, you will find that these objects are crowded a lot, and non-maximum suppression must be used very delicately in these situations. But in general, what it's trying to do is it will take the prediction with the highest confidence score, and anything that is overlapping with it or has a high overlap with it will be ignored. How do we measure the overlap? How do we measure the overlap between the different predictions or the different proposals? Is by calculating the intersection over union between the highest confidence proposal and everything else that exists in the predictions of the model. We spoke about RCNN as the first method for object detection. And basically what it does, it takes an input image, extracts a couple of region proposals, exactly somewhere around the 2000s, a bit more, a bit less, depending on the image. And it does that by using selective search. So we have seen what selective search is. Selective search is just an algorithm that tries to segment the image into different segments based on their colors, texture, intensities, and different metrics. I think there are like 5 or 6 metrics used, but it's not very important. If you guys would like to read a little bit more about that, there is a good article that explains it very well, but it's simple, just basic mathematics. Once you have these metrics to evaluate whether 2 pixels are very similar to each other, you will just use that to combine the regions of the image into clusters. And you just iteratively combine all of these regions together using some greedy algorithm. Greedy algorithm means just we're trying to optimize for a certain metric. After that, we just take whatever proposal we get, we resize the image. So image resizing is something very commonly done and something that you already know how to do. So we resize this proposed region in the image into the same shape that is expected by the CNN. And then we do exactly what CNNs do, something that we are all familiar with. Some of the problems of this article, of this model, as we said, so the training time takes a lot of time because you have 2000 classifications in the same image. And if you have 1 million image, that just is insane. Inference time is around 47 seconds. So that is also very, very large. And selective search is not dataset specific, meaning it does not give good results for the majority of the datasets that we are working with. Fast RCNN was a very, very interesting idea in its own. So basically, the authors of Fast RCNN provided us with a very beautiful trick, basically to save us a lot of time. So the first step is to always segment the image as before using selective search, right? So we use selective search. That selective search will propose to us 2000 regions, but instead of sending each one of these 2000 regions over the CNN, we send only once the whole image. So we take the whole image, send it once through the CNN, and then we do this mapping between, so we remove this, we do the mapping between the regions of this, what is it called? Of these 2000 proposed regions, and we map it into the feature map. This way, we basically save the calculations of this 2000 CNN passes and replace it with just 1 CNN pass. This is a very interesting idea, to be honest, and it's one of the few very creative techniques that were introduced in the field. And the idea is based on, as we said, just saving computations by running once through the CNN and doing the majority of the work on the feature map and not on the image on its own. And this idea of working on the feature maps instead of working on the image will be noticed, or you will see it throughout all the next or future architectures that we will discuss. Now, one problem arises, basically, how do we replace the previous step that we discussed? Basically, as we said, we take the regions, before we send them through the CNN, we must do image resize. Now, the equivalent of image resizing in CNNs for this architecture is to basically take this feature map region. So the feature map region might have different shapes and ratios. And what we do is we send it through the ROI pooling. So we have already discussed ROI pooling. It's a pooling layer that takes any shape and outputs the same shape again and again, regardless of its input. Very similar to max pooling, basically it will take the maximum over a certain region, but in this case, the region is not fixed. So you might have a region of 3x2 in the first, and in the end, you will have a 2x2 region or a 3x3 region or something like that. As we said, so this is how the algorithm finds the mapped version or the mapped location of a object proposal. But this is proposed by selective search. And what we do is we just calculate where its location is in the feature map. The calculation is pretty simple. So we basically take the center of the object. We take the center of the object and divide it by the scale. So, or the stride. Basically what this is, it's the size of the original image compared to the size of the feature map, right? So the feature map is usually much smaller than the original image. And in our case, it is 16 times smaller. So what we do is we basically divide the center by 16. So the X and the Y coordinate will be divided by 16. And there you go, you have your the center of your object. And same thing will be done for the height and width of that object. Now, the problems of fast RCNN is that it's actually very fast, right? So the RCNN part was taking a lot of time for training, whereas the fast RCNN is much faster. And the main problem is noticed here. So the difference between the selective search algorithm plus RCNN and RCNN on its own was not very big before. So this loss of time due to selective search was not something very important for us. So it's something definitely that to be ignored. But in the case of fast RCNN, so you can see that fast RCNN architecture is too fast without selective search, that the difference now becomes very significant, right? So the majority of the time, let's say 92 or 93% of the time of running inference on fast RCNN is the selective search algorithm. So this is something that takes a lot of time. And for us, the best way to move on and continue this research is to basically remove the selective search algorithm completely. And this is what they have proposed with the RPN, or Region Proposal Network. So Region Proposal Network is exactly the algorithm that we have discussed in the start of the lecture, where we said we will be sliding a certain classifier over the image to predict possible locations of the objects. RPN works exactly like that, but it does it with a small intelligent trick. Instead of sliding a full CNN over the image again and again and again and again, we will we will borrow the idea from FastRCNN by simply, let's go back. By simply taking the image, passing it through the CNN once, and doing this sliding operation, right? So our sliding operation, we will be doing it on the feature map instead of doing it on the image. So what is the main difference between these two? Basically, it's time saving. So the first problem is the size of the classifier. If we just compute all of this together, and basically we do it on the image here, for example, and then next pixels and next pixel and next pixel. So we will be applying a full CNN on, let's call this 1000 by 600. So we will say that we will be applying it even more than 2000 times, like 20,000 times, right? So applying a CNN on 20,000 times is very time consuming. Whereas if we send the image once through the CNN and do the search on this smaller feature map, this will give us much better results. Why? Mainly because we can first make the classifier that we are sliding much smaller, because the majority of this hierarchical learning is being done by the CNN. So for us, it's just going to be a linear classifier in here. And linear classifiers, the good thing about them is they are very, very good in parallelization, right? So the multiplication of two matrices is something that GPUs can do very fast. And since it's a small operation that is very parallelizable, the sliding operation part can be also done in a parallelizable way. So instead of sliding it once in here and then sequentially going to the next point, we will do it all at the same time, or we do like half at this first time, and then the next one will be done right after. And this architecture becomes a much smaller architecture and a much faster operation to do than selective search.
Can I have a question?
Yes, go ahead. I love questions.
Yeah, so how does this architecture proposes regions of different sizes where the size of the sliding window is the same? I'm assuming.
Can you repeat this?
We're using a sliding window, right?
Yes.
On each feature map. And if we use this, and for each sliding window, we classify if this region is a region of interest or not.
Yes.
Right. Then how are we going to propose regions of interest of different sizes, like in the.
I really like this question. And the answer lays in two different locations. So the first one, just one thing that you have said, and I need to clarify, we're not, this feature map, as you can see, has 512 channels, right? So once we are sliding, we slide through this, and all 512 channels, okay? So just so you understand this better. So this one is not just looking at the first channel of it, it's looking at all of them at the same time. So this is information number one. And information number two is we're not using one sliding window. We're using different anchors, right, of different shapes. And whichever one is the most similar, for example, to the object, this will be the one that gives you the highest classification prediction probability, right? So basically, the classifier that belongs to, let's check different sizes of them. Yeah, so let's say the classifier that belongs to this rectangular anchor will be the one that has the highest classification prediction, and all the others will be just ignored. Second thing is that we have in here two types of classification. So you see this classification layer, it's only doing object detection. It's not doing, what is it called? Classification, right? So we're just proposing regions regardless of what object it is. And here, if we think about it logically, we don't need 2 times k scores. So k is the number of anchors. Well, we only need just one. Either it exists or 0, it does not exist. But they have specified it as 2, especially because they wanted to have this ability of saying object. Here, for example, so this is the object location of the area which will have a positive activation. And here you have a very strong signal that says no object. And of course, here also you have no object, no object. Let's assume there are no objects in this region. This will teach the, what is it called? Your classifier to be much more precise than what it would have been with just 1k or 1 times 9 scores. Last one is the basically regression layer. So the regression layer, what it will do is it will change the shape of the anchor. So you see this anchor, let's say it's very similar to the shape of the object itself. Let's say the object looks like this. And the anchor would look something like this. This is the anchor we used. What this regression layer will do is it will change basically the shape of this anchor, and it will predict the shape of the original object. Let's say the center of the object was not here. Let's say it was here, for example. And it will change basically the height and width of this anchor. Does that answer your question a little bit?
Yeah, so basically 4K, the 4 stands for the coordinates, like of the corners of the rectangle, right?
Not corners, center / width / height. So X, Y of the center, width, and height.
Oh, yeah, makes sense.
4 coordinates.
Yeah, that answers my question. Thank you.
Thank you. Nice. Very good question. Now let's just come back a little bit and finish it up here. So once we have this classifier that is working its way through the feature map, basically we will have different region proposals. We will not have 2,000, so we will have much less region proposals than with selective search, but these region proposals will be first trained on our data, so they will be more useful for us, and they will be much faster. So it's going to be a much faster operation, and overall this operation will be much faster. The rest of this architecture is exactly the same, right? So we have ROI pooling here. This one as you can see, this is the same backbone used here. So we are sharing some weights. And once we have this feature map, we apply ROI pooling on the selected regions or the region proposals. And then we just send it for classification and send it for bounding box regression. Let me just clean it up. Done. So this is the faster RCNN. It's just RPN plus fast RCNN. So just a quick recap of the family in a whole. RCNN used selective search and sends all the images or all the regions through the CNN again and again. Fast RCNN still uses selective search, but sends the image once through the CNN, and the regions are being wrapped or being calculated inside the feature map, and then using ROI pooling, we just send it for classification. So it's much faster. Now, faster RCNN just replaces the region proposal algorithm, which is selective search, with RPN, and the whole architecture now becomes trainable and becomes neural network based. So it's all distributed or parallelizable. Now, mask RCNN, this is something that we did not discuss in this course, but for the students who took the introduction to computer vision, we already discussed it. We will not have a lecture about segmentation in this course. So just for those who did not study segmentation, what will basically happen in here is that we will keep the faster RCNN architecture and add another layer here, or add another couple of convolutional layers and upsampling layers. What they will do is they will tell you each pixel inside this feature map, preferably each pixel inside basically the image, what does it belong to? So how does it do that? It will take the feature map, only the feature map, and then send it through a couple of convolutional layers or a couple of neural networks, just like some neurons, and do some hierarchical processing basically to find or to build this feature map. So it's just a feature map. If you already know what is an encoder / decoder, this is a decoder part. It will take a feature map and output a feature map. In this output feature map, we're going to have basically a feature map with the same size of the original image. And each pixel in that feature map will contain the following information. So basically you contain the class of each pixel. So the class that belongs to that pixel in the original image. Now, since the classification part is already being done here, so the mask RCNN, this part that is added now, so the mask fully connected neural network predictor, what it does is simply it will tell you whether this pixel belongs to the object of interest or it does not belong to the object of interest. We will see this in much greater detail in the mask RCNN architecture. So basically we'll just look at the architecture, check the layers, check the size of the output, check the size of the input, and all of that information. Finally, we spoke about YOLO. So we spoke about Detectron, as I said, so this is just the implementation of all the previous architectures we have seen. And we spoke about YOLO and how it's doing this 3-scale processing. So the most important part that I would like to remind you guys in YOLO is the following. In the each one of these scales will have a feature map as its output. And this feature map will contain the following information, right? Contain the following channels, right? So this is a feature map. The depth is what we refer to as the channels, and how are channels being computed, basically using different filters, right? So remember convolutional layers. For each one of the filters in a convolutional layer, you're going to have a specific channel in the output. Nice. So just remember what we have here is 3 different boxes. Each one of these boxes corresponds to a different type of anchor. So either rectangular, either horizontal, or vertical. And at each one of these boxes, we will have the following information. First, the bounding box coordinates, or the improvement of the bounding boxes over the anchor. Objectness score, whether there is an object or nope. And if there is an object, we will have a class score of what object it is. What object is it, right? And so basically here, just remember when you are configuring any version of YOLO v4, of YOLO, you must always remember to change the filters or the number of filters in every convolutional layer before these different scales, right? Every convolutional layer before this one must have a number of filters equal to classes plus 5 times 3. So why is this something that is you must change at every step? It's because it's very dependent on your number of classes, right? So by default, the number of classes is 80. But for your case, you're not going to be working with 80 classes, meaning you must change this value again and again when you are training a different architecture or when you are building a new architecture. So basically, this is it. This is the revision of the lecture. Do you guys have any questions about the lecture, right? The theoretical content of this lecture? Yet? If there are no questions, then we could go to the practical part. Remember, for the practical part, we are, or at least for the lab part, we are going to be using RoboFlow datasets. For the homework, you're not going to be using RoboFlow. So RoboFlow simplifies a lot of things for you. And sadly, it's not very practical to use it outside of labs and stuff. I mean, you can use it, but you will have to spend a lot of money. So for us, what we're going to do is we're going to use another service for your homework. And this service does not provide lots of the features that RoboFlow is providing. And you're going to have to do a lot of writing, like just writing a little bit of translation code or transformation code. So just a quick heads up. So for this lab, we're going to use public datasets provided by RoboFlow. So these datasets are pretty simple to use, and they're all following all the types of standards that exist for object detection. Let's choose something like this one, right? So this is a dataset for what? I just want to see some images.
Sorry, why can't we use RoboFlow for the homework?
Well, first, because you guys will do your own annotations, right? So you will build your own data set, very tiny data set, but you have to build it yourselves. RoboFlow does provide that functionality, but it's not very scalable for solution, right? So I wanted to give you guys a solution that you could use if you go to a company, and basically you can easily integrate it with your own current solutions in that company. So if you use RoboFlow, you're going to be a bit constrained to the architectures provided by RoboFlow.
Okay, I see.
Yeah, it's just a bit more challenge for you guys and more flexibility for the people you will be working with. Just if you guys can see, I don't know why they removed this feature of previewing the data. Previously, you could preview the data. So here, as you guys can see, you have just different rabbits, and they're all in perfect rectangles. For us, what we will be training for now is the YOLO v4 darknet implementation. Remember to copy this code, and then you just choose the model. So as we said, we're going to be using YOLO v4 darknet implementation, and here you will find the free Colab that is attached to that implementation. It's very good for like getting started, right? Yeah, so here they are by default working on this data set of red cells, or just like some cells, right? I don't know what these cells are, but they're cells. For us, we're going to be working on something else. So we will still follow their whole code. Let me just run the code first. And yep. Yeah. Yes. There we go. I guess download it here. Oh. Dataset.location. Yeah. Let me just make it like this. Underscore location. Equals. I will explain to you guys what I'm doing here, but I think for those who have already known or have already seen the last lecture or last lab, you already know what I'm doing here. Right, so here, here, and there should be another location here. Dun, 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 dun. I don't see any other location. Yeah, sounds nice. Let's run the training. Run anyway. Now let me just repeat the explanation of the code. So first part is the installation of Darknet. So Darknet, as we said, is just a new implementation or a new C++ based or C based framework for building neural networks. So it's much faster than what you would get from PyTorch. And it's a bit better for those who are going to work on the edge because you can compile it, and some people, like some services, can provide optimizations for that for specific architectures. So that's a bit better than using, again, Python or PyTorch for training your neural networks. What you get is first you will have to check that everything is working and you have access to all the NVIDIA commands such as MVCC and NVIDIA SMI. You will have to find what are the different parameters of your architecture or of your GPU. If you don't find them here, you can easily find them with a Google search. I think all the majority of the architectures or the newer GPUs will be found here. If you have anything other than this, then you will, or you might suffer a little bit to find this information, or you might find it written on your GPU. Let's continue. So far what we're going to do is we're going to bring or to fork or clone basically the Darknet implementation. This is just the code for Darknet. And we're going to basically, here they're removing makefile just to write it again. So here they're writing the makefile again with GPU activated, QDNN activated, and OpenCV activated. So these are by default equal to 0. And if you would like to work on the CPU, just set these to 0. If you don't have an OpenCV implementation or what is it called, library, but for C, yeah, I'm not speaking about OpenCV for Python, OpenCV for C. If you don't have it installed and correctly configured, which is something that is very difficult to do on AWS servers, right? So anything that is like EC2 instances, it's very difficult to install OpenCV again and configure the paths and all of that. But if you don't have it, set it to 0. If you do have it and you manage to install it correctly and figure out all the other paths and stuff, then set it to 1. The next is just to basically set the architecture value to whatever you have, depending on your architecture and your GPU. And beautifully, you just make this library and using the makefile, it's gonna print out a lot of this code or a lot of this output. This means things are going well, right? So don't worry, unless you see something red or something that says error, everything is going well. Now here we are going to download basically the weights for YOLO v4. Now, we will not explain this now. We will skip this part and we will come back to it a bit later on. Here I'm just downloading the RoboFlow data. Oof. I didn't know this one. Yep. Nice. Right. So here we are downloading the RoboFlow data. So you can see there is a validation folder, there's a training folder, and there should be a testing folder too. Too much. So basically here you see the train. Here's the image in JPEG format, and this is the TXT file describing the annotations of that image. We will check an example of each right after we finish here. So now we are configuring or setting up the environment and setting up the different files needed by YOLO v4 Darknet implementation to basically run. This setup of files is very commonly seen, so you might also, so we will see it also for YOLO v5. But basically what you will have is the following: an object.data file that contains the following information: how many classes, how many, where is the training, validation, data, and names, and backup. So here for our case, I'm not sure how many classes that does this architecture have. They don't have anything about it here. Is it just me or their website is getting worse and worse every day? Software, annotate, dataset. I just want to know how many classes do they have. Let's go to these files, and it should be, let's go for validation. Yep, here it is. How many? We just have one class. Okay, so here we just change this into one class. Yeah, so as I said, you're gonna need to create this object.data file that contains how many classes, the location of the training images, location of the validation images, and the location of the objects.names. Object.names is basically a file that contains the names of the classes. That's all. And the location where you want to store the different versions of the trained model, and also the metrics. Here, this is how we are creating this train.txt. It's just basically a txt file that contains the list of all the images used for the training, and this is the list of all the images used for the evaluation. And as you can see, we only put the values for the images, and it assumes that the what is it called? The annotation file is in the same folder as the what is it called? As the image file, and they are all what is it called? They have the same name, basically, as we've seen here, right? .txt, .jpeg, .txt, .jpeg. Make sure that you have this naming convention. And now let's check what they are saying. Cannot create directory. CD make file. Oh yeah, Victor. Because I'm running it again, right? Yep. There you go. Works well. Seems to work well. Works even better. Start the training. Nice. Now the second step is to configure how you want to the YOLO before to train. And this is very similar to the step in training neural networks, where you basically decide on what are the loss functions used, what are the activation functions used, what are the learning rate, or the what is it called? Optimizers parameters, basically gradient descent, what is the learning rate, what is the momentum, what is all of that information that you need to provide, and you define that in here. Let's go to the README of YOLO before darknet together. Let's stay here, so we'll be able to come back easily. Darknet Alexei AB. Here it is, and we go down a little bit. Train, yeah, on your custom dataset. So here he provided a very beautiful to-do list, and just go through it and you will understand the different steps needed, but it does require some training to understand how to read it. So here, first you need to define what is the architecture you would like to use, and we define architectures using basically these different config files. Let's come here, let's go open it again, and here we will see here it is. So these are the different config files. As you can see, there are lots and lots of architectures that you can train using darknet on its own. It's not just YOLO v4. You can train YOLO v2, YOLO, and YOLO v3. But the most important one, of course, is YOLO v4. So here you will find the following names, right? So there is Mish 4x. So 4 is the name. So there is X. There is this new config file. I don't know what they added here. There's the traditional one. There's the tiny contrastive. There's tiny costume, tiny 3L, SAM, Mish, CSP, reorg, BFM. We will speak about that also a bit later. P6, P5, P5 frozen, YOLO v4 custom. So YOLO v4 custom is exactly YOLO v4. YOLO v4 CSP and YOLO v4 X swish, swish frozen, mish, swish, all of these names, right? So these are the names that we have seen. Now, what we are going to do right now is to stop a little bit from the practical part and go a little bit to the theory. So what we will do, we will take the name swish and mish, and we see what these are, right? Swish and mish activation functions. So these are just new activation functions. And as I remember, how they did it is basically train a reinforcement learning model to build the perfect activation function that speeds up the training and provides more stable results. And this is exactly what they have done. Let's just, what is this one? This is Mish, and where's Swish? Yeah, so this is ReLU, as we all know it. Let's just zoom out a little bit. So this is ReLU, as we all know it, and it's a very beautiful activation function, provides very good results. But they have discovered, the people from Google Brain in 2017, they have discovered this beautiful architecture. And how they did that, as I said, is just by training a model to combine different functions to provide the best looking function or the best function for the training. And yes.
So it turned out that this one is better than ReLU?
Yeah, it's very similar to ReLU, but it does have this.
I mean, why it's not so common? Since
it is
really?
very common, actually. Yeah, it's very common both for classification and for object detection. For object detection, it is the most common. So I think even now the custom ones, like the original ones, you will find Mish or Swish. Let's come here. Mish, yeah, it's so common that even in the default one now they're using it, right? So
Cool,
even
cool.
yeah, so here, for example, they're calling it Mish because probably this was the architect. This was like the first time they introduced it, but now they just use it as the default functions, right? Either Swish or Mish. They're very good. Both of them are amazing. And here is Mish. As you can see, the architectures are very similar. The loss functions again are very similar, but they have certain advantages over ReLU because they propose or have better derivatives and have better training, and they don't have this neglection of non-zero values or non-positive values. And of course, they go down a little bit, but for very, very negative values, they completely ignore them. So it's this beautiful architecture that, that adds up to the beauty. So here we can see that the range is around -31 to plus infinity. Some of the advantages of Mish being unbounded above is a very desirable function. So it's unlike, for example, what are the other activation functions that we know?
Sigmoid.
Yeah, unlike Sigmoid, it is unbounded, and this is something that is very desirable. This is something that they have discovered to be very desirable. Let me just turn off the notifications here so I don't get bombarded. Yep. Nice. So as we said, it is unbounded, and that has lots of desirable functions for us, properties for us. Being bounded below is also advantageous because it results in strong regularization effects and reduces overfitting. And ReLU has an order of continuity as 0, i.e., it is not continuously differentiable. And many can cause some problems in gradient-based optimizations, which is not the case for Mish, and it's also not the case for Swish. There is also other architectures or other activation functions that are very commonly used, such as SoftPlus, and they all follow basically the same architecture. Let me just come here. Maybe they have SoftPlus here. Yeah, they have SoftPlus here. Here is SoftPlus, this one. So it's very similar to ReLU, but it does not hit 0 and does not give any negative activations. There is this bent identity, also very similar to ReLU, but it's not bounded from below. Leaky ReLU. Leaky ReLU is good also, but it's not also very optimal because, as I remember, it just continues going down infinitely, but in a slower rate. Sigmoid, not that optimal. TinyH and ReLU, not that optimal. Mish, very good. Swish, very good. So now that we at least know what are these different names, let's go to the next names, which is, for example, CSP or P5 and P6. For that one, we just come here and we will take a look at them. Personally, I don't recommend you guys using any of these models unless you're in a very industrial situation and you have lots of resources. But here are the architectures that we have seen. So scaled YOLOv4 is an improvement over YOLOv4 that provides much better results. And here we can see a comparison between them. YOLOv4 is the gray one. Here it is. Can you guys see my? Yes, you can.
Yes.
So here is YOLOv4. So you can see this is YOLOv4 with a 416 input size, image size, right? This is a 512 by 512 image size, and this is the 608 image size. This is YOLOv4, the basic architecture. And here we can see, not PPYOLO. PPYOLO is not very good anymore. Scaled YOLOv4 is this one, this green architecture. So you can see for the same latency or for the same time or for the same computation expensiveness, you have a much higher results for YOLOv4 scaled. And if you can afford to basically go much more expensively or slow down a little bit your results, but slow down your performance, but improve your results, you can go to, for example, this one's YOLOv4 scaled with 600 by 40 by 640. So this is a bit better. This is the 4x that we have seen mesh architecture. And basically these are the P5, P6, and P7. So here we are speaking with high dimensional images. We're no longer speaking with 400 by 460. We're speaking with an image that contains or maintains as much of its, what is it called? Its original dimensionality as possible. So we're working with very high dimensional images. This is not something that you will be deploying every day. So this is something that is very industrial specific. And just for the person who has not turned off their mic, can you please do that?
I have a question.
Yes.
Why they're not talking about YOLOv5? Because I heard that it's like 90% faster than YOLOv4 and with the same benchmarking. So
it's just a little bit does not have the respect in the research area. We will speak about it and we will see it. It's very good. I used it and it's nice, but it's not very respected because they haven't published an article about it. So they didn't publish it in a journal or in a conference, right? So it was just like, hey guys, we have this solution. It works. Check it out. So there was no peer review. There's a process to propose such architectures, and it should be reviewed by different researchers and basically presented, discussed, and stuff like that. And YOLOv5 did not go through any of these different steps. This is why it's not being compared here, and this is why you might find it kind of attacked in the field. So we will speak about YOLOv5 right after this one. It's a very beautiful architecture. It's very simple. They didn't really present any new architecture or something like that, but they have presented some smart ideas. And the most important part is that they have made it very accessible, right? So made it very easily used. So you're gonna see that it's much easier to use than YOLOv4, mainly because it's built by industrial people and not by research guys, right? So with research, you're gonna have to think a bit, but here it's much better. Now this is done, right? So let's continue this comparison. So for example, currently the best one that is here, for example, it's D7X 1536 here. So this is, I think, efficient det. Yeah, this is efficient det. And as you can see, it's pretty slow, right? It's really slow. It is slow, right? It's super slow. Like it takes one image in 1.5 seconds, even more. But its results are very good. YOLOv4 scaled provides the same performance and even better at a much slower or much faster time. And this is why YOLOv4 scaled is very important. One of you guys could present to us YOLOv4 scaled and what its differences are compared to YOLOv4 and YOLO in general. Another one is very beautiful here. So you can see SwingT, right? Swinty, this is also an architecture that we will be speaking about hopefully after 2 weeks. We will speak about this architecture. It's very beautiful. It's open. It's not, as you can see, some people are saying it's the best, but others are using it and comparing it, for example, with YOLO v4 and stuff which have been proposed much earlier and have been evaluated much deeper. And they're saying it's better, but still it's a new field of work that is not really based on CNNs and stuff like that. So it's something that is a bit revolutionary in the field, and it definitely is worth looking into it if you'd like to continue doing some research, for example, for those who are going for masters and stuff. Yeah, I think that's it. So we have seen the different CSV files, config files. Personally, for the lab purposes and for the homework purposes and for your project, always use YOLO v4 Tiny because it's the smallest and it trains on Colab in less than an hour. So that's very good. This is good enough for us and it does provide very good results. So now we have selected the architecture, which is YOLO v4 Tiny. The main difference, YOLO, right? So you see here, this is the first YOLO, this is the second YOLO, this is the classification layer or the object detection layer, and this is the next one. Remember when we said in the theoretical part or the lecture part, YOLO works on 3 scales. Well, YOLO Tiny is a smaller version of YOLO that works only on 2 scales. This is why it's tiny and this is why it's much faster. Of course, you're going to sacrifice a lot. You're going to sacrifice a lot in terms of results, but you're going to gain also a lot in terms of speed and training speed and basically all of the things that you might need. So for example, inference speed, which is very important for certain industrial applications. The first part, this is the network part. So here, all of this is about the training algorithm or the information used for the training, batch size, subdivisions, width, height, number of channels for the input. So if you have more than 3 channels, RGB or something like that, you could change that here. There are some people working with me on, I don't know the name of it. It's called LiDAR, not LiDAR, RealSense camera. I think the guys from robotics, they know this, right? So basically you don't get just RGB channels, but you get some depth channel also. And you could incorporate that here by changing the name or changing the number of channels. Momentum, decay, angle, saturation, exposure, and hue. All of these are used for the what is it called? Image augmentation part. Yes, and this is being used. This is being used for the training part. Learning rate, burn-in, maximum number of batches, policy, steps, and scales. This is used for basically this, all of that together represents what we previously used to speak about the number of epochs for the training. So now we're not speaking in epochs, we're speaking in iterations, and we're not calling them iteration, we're calling them a batch, right? So here, number of iterations that you have previously seen, for example, for those who work with TensorFlow previously or TensorFlow 1, it did not speak in terms of epochs, it was speaking in terms of iterations. And just the difference for those who don't know, an epoch is passing through the data set, all the data set once, whereas an iteration just means one step of gradient descent or passing through one batch of the data. So an epoch usually contains like 200 iterations or something like that. This is just a very good comparison to keep in mind because we will see this in YOLO v5, it's not the same. So again, max batches is the number of iterations that you will be training for. And a very simple rule of thumb is to have the following: 2000 times number of classes. This is a very simple formula, always keep it in mind. It does give very good results. If you go above, you might overfit. If you go under, you might underfit. The researchers have tried different values, and this was the value that gave good results on different data sets. The rest of it, useless, right? So the rest of it is just convolutional layers, see some batch normalization, number of filters, the size of the filter, number of the stride of the filters, the padding, and the activation function. So you can see here leaky ReLU, leaky ReLU, leaky ReLU. And yeah, the routing, whenever you see this route layer, it means, let me just pull up the lecture and show you guys. Yeah, here it is. So you see these skip connections, or these copying the convolutional feature map from a previous layer to a next layer. This is what's happening here in the config using these routing mechanism. Max pooling, you already know what max pooling is. Convolutional, another route, convolutional, convolutional, convolutional routing, convolutional max pooling, convolutional. Now we are entering basically the first this path, right? So we were speaking in this path. Now we are going down this route. Let's go to yeah, come back again. So again, just convolutional, 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 and here is what is very important. So whenever you see a YOLO layer, you will have lots of information here. So for example, how much do you focus on classification? How much do you focus on what is it called? Intersection over union. This is the intersection over union loss. Just lots of hyperparameters that you could play with. Non-maximum suppression, the beta for non-maximum suppression. So basically, this is what we have seen as the threshold for intersection over union. Scale of X and Y, jitter, num classes, anchor sizes, and the mask. Most important part here is number of classes, and most important part here is the number of filters. As you have seen in the lecture, here, the filter formula for the number of filters for anything that is before, right before a YOLO layer is the following: classes plus 5 times 3. So in our case, we have how many classes? We have just one class, right? So one class in the following formula: 1 plus 5 times 3 equals how much? 6 times 3, 18. So here we should replace this value with 18, and we should replace this value with 1. And we should repeat this process for the following layer 2. So this is the second scale of YOLO. Change the number of classes to 1, change the number of filters here to 18. Of course, the number of filters in here do not change, only the last convolutional layer before a YOLO layer. If you have multiple YOLO layers, then you must do this for each one of them, right? And this is it. We have seen how the config file looks like. Now let's continue. Let's continue here. So now that we have the config file and we understood how does it look like, the second part is to get the pre-trained weights. We will speak about the pre-trained weights later, but let's continue here first. First thing is to create these different, what are they called? Yeah, this is for the, I already covered this, right? So how to create the YOLO before config files, or how to change the config files. Basically, you change the number of batches, subdivisions, max batches, number of steps. This is the formula for it. Size of the architecture if you'd like to have, depending on what pre-trained weights you're using. Number of classes, number of filters. Here's the formula. This is another type of YOLO layer. Not really interested in that. And that's it. Second step basically is to create this object.names file with the object names in each one in a new line. Next step is to create object.data, as you have seen. And basically here you put the number of classes, the location of the training images, location of the training validation images, object.names location, and the backup location. Put the image files in this location. And yeah, this is just for how the labeling looks like. The labeling should be the following. first value of the first object in that image must be the class index. Second value is the x, or the absolute center of, no, here. So the relative center of the image or the object, the relative center of the object, but y coordinate, the relative width, and the relative height. So what are they relative to? Basically the image width and the image height. Download the pre-trained weights. So this is a place where you can find the pre-trained weights, and yeah, and you start the training. Now, the final part is to speak about where do you find the pre-trained weights, and this is a bit confusing sometimes. Pre-trained models. So here you'll find a list of some pre-trained models. It's not very exhaustive. There are not all the possible pre-trained models that are provided by ULOv4. I don't know why they don't always put them here. But here, for example, you find ULOv4 Tiny. Here are its performances, and this is the weights. ULOv4 basic config. Here are the different weights for it. ULOv4 CSP. Here are the weights for it. MISH. Here are the weights for it. CSP Swish. Here are the values for it. CSPX Swish. Here are the values for it. P5 and P6. So you can see that P7 is not here, and other architectures are also not here. Usually, how I personally do it is I go to these releases, and then I go to the assets, right? So for each release that they make, they always put in new releases, and usually you find the weights in here. So for example, ULOv4 new, I haven't seen this before, but I have no idea what is the difference between these two. But yeah, they uploaded it like 10 days ago. That's cool. So these are different weights that you can look for. If you don't find it here, check a different release. You probably will find it there. So this is it for ULOv4. Now let's go to the paper of ULOv4 and understand what did they add, right? So here we'll really abstract. So I think we already did a how to read a research paper. So first to speak about read the abstract, let's read it together. There are a huge number of features which are said to improve CNN accuracy, practical testing, combination of such features on large datasets. Some features operate on certain models exclusively, for certain problems exclusively, and only for small-scale datasets. Whereas some other features, they're very generalizable and can be used in different problems. This is what they're saying, and I have dyslexia, so I don't know how to read well, but let's continue. We assume that such universal features that are used always are weighted residual connections, WCR, RC, cross-stage partial connectiveness, CSP. Remember CSP from before? Cross-mini-batch normalization, self-adversarial learning, and MISH activation. So already we know MISH activation, and we have heard about CSP. We use new features, all of them, basically, and mosaic data augmentation, drop block regularization, and CIOU loss, right? So it's C intersection over union loss, and combine some of them to achieve state-of-the-art results. So as you see, the architecture is exactly the same as ULOv3, but they added all of this beautiful training methods, let's say. Let's just completely ignore all of that. Different information can be found here. So for example, the input image, what does it look like? Could be image pyramid, an image, or patches. This is very important because there are different types of models. Different backbones. Some people use, for example, VGG, ResNet, SpineNet, EfficientNet. And I think the best one is not here, right? So the best one is feature pyramid networks. And not feature pyramid networks. Let me check them. Pyramid networks. Yeah, feature pyramid networks. Okay, so it's correct. Feature pyramid networks are very beautiful, and this is now the default being used. I'm not going to go into the details, but here you can already see the details. Basically, what you have previously, you would take an image, send it through some convolutional layers, and then send it for classification or for the prediction part. Here it is, right? So take an image, send it through a couple of convolutional layers and send it for prediction. Now what they're doing is basically, I think they're doing D, right? Feature pyramid networks. Yes. So here the prediction is being done at different scales. And here you can see that we have the up and down path, right? Similar to what you would expect in UNet for those who took the image segmentation course. But yeah, so basically we will be doing the prediction on different scales, and this provides better or more important, more interesting convolutional feature maps that are useful for both segmentation in feature steps or object detection in feature steps. Let's come back to our beautiful architecture here. So first information is bag of freebies. What is bag of freebies? So usually conventional object detector is trained offline. Therefore, researchers would always like to add or take this advantage and develop better training methods which can make the object detector receive better accuracy without increasing the inference cost. So basically, the bag of freebies is anything you add for the training that does not change anything for the evaluation or for the inference. So we call these methods that only change the training strategy or increase the training cost as bags of freebies. And here they will give you a couple of bag of freebies. So for example, a random erase cutout, or they said also something about mosaic augmentations, right? So this is also something pretty cool. And for those who are interested in more, you can find different bag of freebies introduced here by the authors. Bag of specials, on the other hand, for those plugin models and post-processing methods that only increase the inference cost by a small amount, but can significantly improve the accuracy, we call them bag of specials. So bag of specials, they increase the inference time, but not by a lot, but hopefully they would increase, what is it called? The overall performance of the model. And here you'll find a very beautiful list of what these architectures are, or what these bag of specials are. For example, different activation functions and all of that. Here you'll find a very beautiful comparison of all different combinations of all of these things. So bag of freebies and bag of specials, which ones they chosen, which ones provided better results, which ones did not provide better results, and all of that. The architecture here is very beautiful, and the explanations are amazing. For those who would like to get better information about the article of YOLO-v4, definitely read the article here. It's very simple, very easy to read, very easy to skim through. You don't need to read it in detail. You can just skim through it and you will find all the information that you would like to find. Yeah, so that's it for YOLO-v4. As you have seen, we have done all the configurations, and now we are doing the training. Yep. So here's the training. We have done 150 iterations so far. It does take a lot of time. For example, it takes 7 hours or even more than 7 hours. So probably 8 hours to train YOLO-v4 normal size. That's why I always propose to you guys to work with YOLO-v4 Tiny, because YOLO-v4 Tiny is much smaller and it doesn't take a lot of time to train. And yep, that's it. Let's stop this. So this is it for YOLO-v4. I hope this was a good introduction to the architecture. Now let's go to YOLO-v5. Do you guys have any questions before we go? Do you have any questions about YOLO-v4? Anything?
Not about YOLO-v4, but could we have a break?
Yes, yeah. Yeah, I think we took it a bit too far. Let's take a small break, like 10 minutes or 5 minutes. Let's say 10 minutes, and come back right after, and just so you could simulate a bit better.
Thanks.
You're welcome. Thank you. Hey guys, I hope you guys are back. Let me turn this feature on. Okay, looks good. I hope you guys rested well, and I hope you're ready to now speak about YOLO v4. The final architecture we will speak, YOLO v5, I mean. The final architecture we will speak about, or the final model we will see, is the simplest, which is a Detectron implementation of faster RCNN and mask RCNN. It's a very beautiful architecture, very beautiful implementation that simplifies a lot of the stuff for you. So all of these problems that we are seeing right now, kind of are solved in Detectron, and that's why I always use it as my baseline for anything. Basically, it just takes less than 5 minutes to get it completely configured and start to run. Yeah, so let's get to it. Nice. So you guys can see my screen. Let's go back, and now instead of going for YOLO Darknet implementation, we will go for YOLO v5 PyTorch implementation. Continue. We get the code. Here's the code. Copy it. Choose the model. Remember, we're going for YOLO v5 implementation in PyTorch. If you would like to see a video of a dude doing some processing on it, very cool videos. You guys certainly cannot hear it, right? Yeah, so here he will explain lots of stuff about how to use YOLO v5 and about how to use RoboFlow. Always very cool videos here. The same thing, for example, for YOLO R. He will explain it to you, and we'll give you some good introduction to it. Scaled YOLO v4. YOLO v4 Tiny, I love it. It's the best one, but nothing there to explain. So now let's go for YOLO v5. So first, YOLO v5, just a bit of history. YOLO v5 has been proposed by this company called Ultralytics or Ultralytics, and they are very famous in the field of computer vision. They provide, I think, making artificial intelligence easy for the world. So it's basically a company that provides artificial intelligence services to other companies, and they have created YOLO v4. YOLO v5, sorry. So here, if we come to the YOLO v5, first thing you will notice there is no article about YOLO v5. So YOLO v5 is a family of object detection architectures. All models are pre-trained on the COCO dataset and presents Ultralytics open source research into future AI methods, but they have not published this in any journal or any conference, meaning they have not been peer reviewed, and they are lacking on the trust department. Let's see. So here, for example, you see how to train on a custom dataset. There are some very cool tips for how to train it. Weights and biases locking. So weights and biases are very beautiful also. What is it called? Website. I hope they have like a link for it. If they don't, then we will just go for it. Yeah, they don't have to. So weights and biases is a cool website that allows you to check how your training is being done. Why is it? There it is. So just to track your progress, track your hyperparameters, your metrics, the training losses, training, all of that information, you can visualize it here. It's pretty easy, already integrated with, I think, PyTorch, TensorFlow, Darknet, all of these models with just one function call in the start, they would be already getting or loading all the information that you need to visualize all of these beautiful things. So weights and biases, you could check it out. Yeah, ONNX, this is also a very important part. TF Lite, ONNX, Core ML exports. So these are very important places also to take a look at. So ONNX provides a functionality or the ability to basically take your model, convert it into a version that is kind of universal, optimize it a little bit, and then you will be able to provide it with a runtime. So this is called the ONNX runtime. It's a long story, but maybe we could have like a final lecture about how to deploy all of these different architectures in all different locations. And in that lecture, we would speak a bit more in detail about TF Lite, ONNX, and all of these different technologies. They're pretty useful. Useless. Right, yeah. So here we see their own explanation of their own comparison. So there's the YOLO v5 version 6. This is the new version that they have provided, and they're saying it's much better. There's no official comparison between them and YOLO v4. Official comparison means that the same person did the training for both and provide the results for both. You can take the results from here and compare it for the results with them from YOLO v4, but that's not a very good comparison, right? And as I said, there are no public articles that speak about YOLO v5 in detail, but you could definitely find YOLO v5 version 6 is here. So let's see if there is something here. House train YOLO v5. I really couldn't find any good article that describes the improvements of YOLO v5. Mainly their improvements, as I read, are not very big, but they could have provided us with a cool article to check it out, but they didn't. So in this notebook, we will do the following. So we'll install YOLO v5's dependencies, much easier than, of course, making any C library. So this is easier for you guys if you're going to work on your own projects, so on your own laptops, not on Colab. Download basically our dataset, write the configs, run the training, evaluate, visualize, and then use the stuff. So here, simply, we are going to run anyway. Clone the repo of YOLO v5 from Ultralytics. We got inside there, and they have chosen a specific hash or a specific Git commit to use, mainly because they don't really want to risk anything between RoboFlow and Ultralytics changes. Here, pip install the requirements as you would do with any other Python library. So it's a bit easier than what we have seen with YOLO before again. Now here we're going to download the data. So remember, I took the download code from RoboFlow. And yeah, dataset location. I hate this new API that they have added. Equals like this. Yeah, much better. And I think we could just replace all. Ta-da. Yep. With the following. Oh, there are not lots of. Okay. Login. Let's say replace all. Done. Yep. So we're accessing it correctly. Done. Let me just start the training. Make sure there are no errors. Weights and biases here. Nice. Okay, there is an error. Dataset not found. Content valid. Okay. Dataset location. We are in YOLO v5. So this one should be correct. This path should be correct. Let me check it out. Oh, sorry. Add data.yaml, yellow A5. Oh, there's nothing here. Where was it? Here it is. So this is for the model. And where is the one for the data? Here it is. So this is correct. Data.yaml. Ah, here it is. Okay, nice. Let's delete this. Let's delete this. Save this. Run again. Okay. Let's just wait for one iteration, just to make sure there are no errors. Yep. There is an error probably somewhere. Let me see. Okay, found. So this is good. Good, good, good. So sounds like it's good, but it's not training for some reason. I know. This is weird. Correct. Correct. Let's do some debugging. YOLO V5. Usually you don't have this error with Robo. Ah, I think I got the error. Yeah. Let me check. Number of classes seems correct. YAML file is correct. Yeah, sounds cool. Ah, here it is. Let's see if they have changed it. Number of classes, is it correctly being read? Make sure that this is correct. It's 1, so this is correct. Correct, 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 correct. Makes no sense why the training isn't being done. Okay, so for some reason previously, either I stopped it or something happened. Yeah, it's cool. Yeah, good. Now let's restart then from the start and check the code. Yeah, so this is quite optional. So just to make sure that there are no problems from Ultralytics that maybe somebody pushed some code that doesn't work and you don't want that in your results. So you could go back to this working code. We know that this is working code. We could keep it. Installing the requirements, getting the data, entering the repo. Here is the first thing that you guys should remember. So basically, RoboFlow now uses this API. You don't need to copy basically this repo, this code to download the data anymore. if you have a account in RoboFlow, then you have your own API in here. You just take whatever workspace it is, the project you're working on, the version, and you download whichever version you would like to download. For example, if you're working on YOLO v5, download the YOLO v5 version. Or if you are working with YOLO v4, you download the YOLO v4 version. So it does simplify things a little bit for the users of RoboFlow, but since we want to make this, we want to make the lab a bit as independent from RoboFlow as possible, so we're gonna do the following. So instead of having dataset.location, I just set this new variable to the current repo, and then just completely remove anything related to dataset.location and just replace it with this variable. The code should work pretty easily. So the first change is, or the first difference is this: instead of having some TXT files and JSON files to describe the data, now we have this .yaml files. So let's go for the first one. This is the .yaml file that describes the data set. Here you have the validation data and the training data, number of classes, and the names of the classes. Previously in YOLO v4, this was in a separate file, right? Now it is a list in a YAML file. So this is just one difference. Second difference is how the labels are made. So here we come, for example, to labels. First thing, you see there is no, the images and the labels are not in the same repository, unlike for YOLO v4, but the names should be the same. So for example, 2019, 2019, so the names should be the same, but they're not in the same repo. One is in images, one is in labels. Now the label itself, as you can see, very similar to what we have seen in YOLO before. First is the class index, X relative, Y relative, width relative, height relative. So exactly as we have seen before. Let's close this long file. Yep, now how to configure or to define the configuration of the model's architecture. One way you could do it is to take the models here. Let's see, this is YOLO. Sorry. Yeah, this is the YOLO v5L, large, YOLO v5M, or medium, YOLO v5 small, and YOLO v5 extra, extra, extra large. For you guys, you should focus on YOLO v5S. It's the smallest, and as we said, for the purposes of the lab, it will work very well. So here you can see things such as the anchors. This is the backbone, and this is the YOLO v5 head. Some of the names you'll find are very similar to what we have seen previously. Some upsamplings, convolutions, CPP, SPP, we have seen those. Yeah, seems to be like a typical architecture of YOLO that we have seen before with a beautiful addition. And here you will see the code that basically reads through this and creates different functions, right? Maps them into different, what are they called? Python or PyTorch values. Here you see, for example, non-maximum suppression. Here's the algorithm of non-maximum suppression and stuff like that. Yeah, you could definitely take a look at it. And the best thing about this PyTorch implementation, it's easy to do research on it. Unlike the darknet one, if you'd like to change the architecture and add some code, you're going to have to write some C++ and stuff like that. And I don't like these things. But for PyTorch, basically you can just come to, to any of these functions, to parse the model, for example, add a new type of layer that you would like to add, and there it is. If you would like to change something with the non-maximum suppression, just go to the function of non-maximum suppression and change it. So it's much more flexible. For example, this is the X version. This is the S version. It's much smaller. And a number of classes, you must change that. The rest, it's easy. And okay, nice. Yeah, so as I said, there is the M, L, X, and S, and the best one is the S version. This is what I like to use. It's the smallest and the fastest. Here, only difference that you will have to do is, of course, to configure the number of channels, number of classes. All the rest is being done automatically, so you don't have to manually change the values each YOLO YOLO classification scale. So that's much better. And yep, so here it is. We're setting it down and you start the training directly. As I said, so YOLO v5 is much easier to use or much more logical to use. So much faster to train, but I'm not sure if it does provide better results than the others. So here, for example, we see, yes, epochs. So here again, we're speaking in terms of epochs and not speaking in terms of max batches or iterations. So this is something good, more logical for people coming from PyTorch background. And the rest is pretty basic, right? Batch size, image size, dataset location, the config that you would like to use. So for example, I would like to use a custom YOLO v5 small or something else. And this is where you would like to cache your results. Usually in the end, you will have all of these beautiful architectures that are giving you the different validation losses and stuff and different implementations. But this is pretty useless. For us, I think we should, do you guys have any questions about YOLO v5 so far? How it's trained, maybe the configs, the data set, how it should be, anything like that. You're going to answer a lot of questions when you are working on your homework, so that's okay. Yeah, the homework is going to take a lot of time, so be prepared for it. And yeah, that's it. This is YOLO v4, YOLO v5. Now, the next step of our lab is to speak about mean average precision. So let me just stop the sharing and locate the mean average precision. Let's share the screen. And this one, yeah, this is the one. So the best way to really study mean average precision is through these two articles, and they're actually very good. Basically, this one is more intuitive. I find it's better. And once you finish this explanation and you understood basically how the mean average precision is being created, you could take a look at this one to get more in-depth understanding. So first, let's go through this one quickly. So to evaluate any object detection model, both object detection and even for image segmentation, for models such as RCNN based or YOLO based, mean average precision is very, very much used. So it's the default metric for evaluation. And in order to understand it, we should first focus on average precision in the terms or terminology of classification. Once we understand it in classification, we will just introduce another layer of complexity on top of it, and that would give us the mean average precision for object detection. So for example, this is our true labels. This is our predicted scores. Let's say the threshold is 0.5, right? And this is our results. First value for comparison is usually the, what is it called? Accuracy, right? So the accuracy would be how many of these predictions correlate with the true labels, right? Now, another way of seeing things is through precision and recall. So precision and recall are different ways of, what are they called? Interpreting a model's results. So let's just get what precision is and what recall is. For some reason, I don't find it here. Let's add them, or let's look for them. This will be useful. Precision Yeah, here it is. Yep. Yeah, so this is just like another, like a similar article that instead of speaking about mean average precision, it speaks about precision and recall first. So let's go through it quickly. We just need, this is accuracy, here's precision, right? So precision is calculated as the ratio between the number of positive samples correctly classified to the total number of samples classified as positive, either correctly or incorrectly. So this means how precise is the model. If the model tells you this is a positive class, if the model tells you this is a dog, how precise is that decision or that prediction, right? So we want something that is very precise, meaning if it tells you, especially for precision, is very important, for example, for investments, right? It tells you that this, this stock is very useful. You don't want it to give you all the very useful stocks, but if the model does say this is a useful stock, it should be a useful stock. So we're trying to increase the precision of the model, meaning we try to increase its correctly positive classes over all its positive classifications. So here we're focusing more on the predictions of the model, right? Whereas for recall, let's go down a little bit. Yeah, whereas for recall, we're kind of seeing the same thing, but from a different point of view. Here we are focused on how many of the truly positive classes are we actually detecting correctly, right? So it's true positive divided by true positive plus false negative. It could be very useful to kind of see how these two values are overlapping or changing. So let's see, this is our predictions. Class like this, and like this, for example. And here's class number 2. This is negative class. Depending on what value for the threshold we will use, so let's say this is the threshold. So this is the threshold. Can somebody tell me what is the accuracy of this model? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8, we have 8 instances. What is the accuracy of this?
Or number 2,
How much?
like 0.5.
0.5, let's see. So 1 is correctly classified, and 4 correctly classified. So it should be 6 out of 8, right? This is misclassification. This is misclassification. All the others are correctly classified, correct? Do you guys agree? This is the threshold. Class number 1.
Yeah.
Class number 2, or class number 0. Nice. Now let's calculate the precision. Precision means everything that has been correctly or positively classified. We will only be considering everything that has been positively classified. How many of them are actually positive? So in this case, two out of 2, right? Now let's go to the recall. The recall would be a bit different, right? So we have this, and this. So we have 4 positive classes or 4 positive samples. How many of them were actually predicted as positive? 2. So here we see the recall is very high, the precision is very low. Now let's change this and go for another. So this is our new threshold, right? So the threshold now is a bit lower. In this case, how many positive classifications do we have? Let's, yeah, it's here. Huh? Yeah, it's here. How many positive classifications do we have, or accuracy? Sorry, how many, accuracy do we have? We have something divided by 8, 1, 2, 3, this is false, and 1, 2, 3, this is false. So it's still 6 divided by 10, by 8, the same accuracy for different thresholds. Now let's see which one has higher precision and which one has lower or higher, what is it called, recall. So here, precision, let's start for the precision. How many did we predict as positive? We predicted 4 samples as positive. How many of them are actually positive? What should I put here? Remember, precision. True positives divided by all that is predicted as positive. I cannot say anything. There is a fire alarm in the second row. Oh, okay. Cool. I love that alarm clock, right? That's like, yeah, it was nice. So basically there is 3 divided by 4. So you see, 3 are correctly positively classified and 1 was classified as positive as an error. Now let's go to the to the recall. In this case, the recall should be a bit higher. So how many do we have as positive? 1, 2, 3, 4. Still we have 4. How many do we have as correctly classified as positive? We have 3. So we can definitely see that the recall increased when we lowered the threshold, and we can see that the precision decreased when we lowered the threshold. So this tells us that depending on having different, depending on the threshold that we choose, we will have different values for precision and recall. And this is where we get the precision recall curve. The precision recall curve is a simple function or a simple curve that is created by shifting the threshold into different locations, right? So first, let's say we have a threshold of 0.1, calculate precision, calculate recall. Go to threshold of 0.2, calculate precision, calculate recall. Go to threshold of 0.3, calculate precision, calculate recall. And at each calculation, you just come here and put the point of interest. So here, for example, we have the following points, right? So point number 1, probably another point in here, point in here, point in here, a point in here, a point in here, and a point in here. So these are the different points that we got from different thresholds for the predictions. And from here, we just get the beautiful, the beautiful precision recall curve. So this is how we create the precision and recall curve. From here, one way to summarize this precision recall curve is a metric that you guys are already familiar with, or something that is called area under the curve. So AOC, basically it will just calculate the size of this area. If it is a big area, this means the model is very good and it's very correct and sure of its predictions, right? So the model always gives you 100% precision, 100% prediction score, or 0% prediction score. And whenever it says something, it's always accurate. So in that case, we will have a precision accuracy or precision recall curve like this. This is the perfect model. Whereas our model is not very perfect. We're just trying to get as close as possible to this perfect model. So the higher this area under the curve is, the better for our classification. So one way to summarize the precision recall curve is the area under the curve. Now, another way of summarizing it, of course, is F1 score, but we don't really worry about that one. Now, another way of summarizing it is called average precision. From the name, you can definitely understand that we are going to take the average of different precision values, right? So we take precisions, we take all the precisions throughout different thresholds, and we take their average. Now, this average, as we have just said, does not take recall into consideration. But the real one in here that we will see will take recall into consideration, and the recall will be considered as the weights of the average. So this is a weighted average precision, and the weights are calculated like this, right? So the weights, so as you can see, it's just a summation over the different precisions. The different precisions are multiplied by the different by some function of the recall, right? So this is the weight. It's a weighted precision. Yeah, it's just a weighted average precision. Now the weights are the following. The weights at step K are equal to recall at step K minus recall at the next step. Now, first question is, how does the recall change throughout the learning, right? So for different steps, how does it change? Here, recall is
0.
nice. And as we are going,
It's increasing.
nice. So if we go for recall at K, it's let's say 0. Recall at K plus 1, it's minus 0, or it's sorry, it's let's say 0.2 or 0.3, right? So this minus is always going to have a negative value, and that's not logical, right? So this is not how we are doing it. Now, if you remember when we saw here with the different thresholds, the first thresholds or the lowest thresholds give you the highest recall, whereas the yeah. So let's go for this in this function. So remember, what is recall? Recall is how many of the positive classes are being correctly classified. So if I have this positive class like this is the positive class. I take the threshold equal to 0. All of them are corrected. All of them are predicted as positive, meaning that the recall will be very high at step number 1, right? So unlike this, what is it called? Unlike this curve, so this curve kind of gives you the information that this is the first recall and this is the last recall. It's actually inverse, right? So this is the first recall. This is the recall you get at threshold equals 0. This is the recall you get at threshold equals 1. And this is, for example, the recall you get at threshold equals 0.5. Okay? So this is the first threshold. This is the last threshold. It's pretty important to check how these are calculated. So first threshold is always very big. Next recalls will be lower and lower. But the difference is always going to be a value between 0 and 1. And all of these values will yeah, so all of them, or these differences will always sum up to 1, right? Why do they always sum up to 1? We have the following, right? So we have 1, and we have another step in here, and another step in here, another step in here, another step in here, another step in here, and we have 0. So what we are doing is we are taking this step as the weight, and the summation of all of these steps, or the differences in all the recalls, will be equal to 1. So this is just like a visual proof of the theorem, but if you guys would like to calculate it a bit mathematically, you can easily prove that the sum of recalls are always equal to 1, and it should be something like this, right? So recall at K minus recall at K plus 1 plus recall at K plus 1 minus recall at K plus 2. And this will remove this, will remove this, will remove this, and it just becomes 1 minus 0, and that is equal to 1. So this is like the mathematical proof, and the visual proof, we have seen that before. So this is what we are considering as the weights for the average precision, right? So, and the average precision is just the precisions throughout different thresholds multiplied basically by their weights, and their weights is just the increase or the decrease of recall in that step of threshold. So again, what is average precision? It's just another way of summarizing the precision recall curve. So we have either area under the curve or we have average precision. Both of them are very similar. For the area under the curve is taking this multiplied by this, right? Plus this multiplied by this, plus this multiplied by this. So it's very similar basically to the same thing we have been seeing. It's very similar to the average precision. And it basically is summarizing the what is it called? The precision recall curve. So average precision is a way to summarize the average precision curve, the precision recall curve. And mean average precision, before we go into the intersection over union, mean average precision is basically the average precision. So we have average precision for class cat, average precision for class dog, average precision for class horse. Take the mean of all of these and you have one value that is called mean average precision. So this is mean average precision, but what we have been seeing so far is mean average precision for the classification. Now let's go see what mean average precision is, but for object detection. And before we go any further, we must introduce intersection over union and how can we use it, right? So this is the ground truth bounding box, and this is a predicted bounding box. So depending on, let's come here, let's zoom out a little better. Yep. So this is intersection over union. You guys are already familiar with it. And here are just different intersection over unions. So this is intersection over union is very slow or very low, 0.2. Intersection over union is kind of acceptable. And this is a very high intersection over union with 0.9. Sorry. Yeah, to calculate the intersection over union for an image, you need the ground truth box and the predicted box. And from the intersection over union, we will be creating the following. So we will be creating this negative and positive, right? If the intersection over union is bigger than a certain threshold, that means we have a positive classification. If it's lower than a certain threshold, then we did not predict the bounding box correctly. So yeah, logical, right? And from here, we convert the problem of object detection. We convert the problem from being bounding boxes into whether these bounding boxes are correct or not, right? So now we converted it from being coordinates and things like that into positive and negative. Once we have positive and negatives, we just go back to our original, to where we started from the start, right, from here, and start calculating the precisions and recalls at different thresholds, and then calculating the average precisions and all of that. So as I said, once you understand mean average precision for classification, the only thing you will need to do to understand is how can we use intersection over union to convert basically object detection into a classification problem. And basically, if an object is correctly, is correctly predicted, meaning the intersection over union between the ground truth and the prediction is quite high, we accept it as a positive classification, so it was correctly classified. If it's not classified or it's intersecting with something that does not exist, right? So it's 0, then in that case, we give it a negative classification. And from here, you can easily find the true positives, true negatives. True negatives don't exist, so this is why we use it. True negatives don't exist. And false positives and false negatives. Using these values, you can easily classify, or you can easily calculate the recall, calculate the precision, calculate the precision and recall at different thresholds, and calculate the average precision. Once you have average precision for each class, you calculate the mean average precision for all the different classes. So mean average precision for the different classes. So it's just the mean over the different precisions, average precisions. So I hope this small introduction was quite useful for you guys to understand what is average precision or what is mean average precision and how do we use it for object detection evaluation. Do you guys have any questions so far? And if you don't, we can go to the final part of the lab, which is speaking about mask RCNN and faster RCNN. Any questions so far? Or a break? No questions. Nice. So I will send you guys these links for the people who would like to read them again. computer vision, deep learning. And I will upload basically now, now that we have finished both the lecture and the lab, I will upload them on Moodle with all of these different links that you might find interesting. Nicely done. Ooh, Detectron 2. Yeah, we will just speak quickly about Detectron 2 and how can we use it to train MaskRCNN or FasterRCNN. We will not take even 5 minutes, right? It should be very quick. After this one, we take a quick break, come back, give you an announcement of the second homework, and we start the individual communications with the different students, okay? Let's run. It's a PyTorch library, so first thing you're gonna do is to install it, right? So you install PyTorch and all of its dependencies. This is just some loading of the different modules. Why is it not installed? So here you're gonna find a small error that will arrive. So we will not continue until we finish this error. And it's a very simple error, basically. Some library is by default used, or an old version of that library is by default used in Colab, and PyTorch or Detectron does use a future or a newer version of that library. So that creates a small conflicts between the runtimes, and just restarting the runtime and loading the new version would solve that problem, and Detectron would work very well. If you don't do it, it will still work very well, but you will have a problem of visualizing the results, so the visualizations will not work. You can choose. Yep, done. So it gives you already this button, and it explains the problem and what is the problem. Nice. Now that it's done, nothing you really need to do. You already have everything installed. We load up just a test image. We have already done this lab before, so we're going to go quickly. As I said, you create a config. Either you use a config file, which is a YAML file. We've seen how these config files look like. Very similar to YOLO v4 and YOLO v5. So everything that you would expect to find here, or everything we have explained there, is the same thing in these YAML files. So here you can see that it's not using, for example, VGG or ResNet. It's using FPN, as we have spoken about before, which are feature pyramid networks as its backbone. And now it's downloading the model. Nice. You take that, what is it called? You take the config and all the changes that you have made. Sorry. And you create this default predictor, and the default predictor now you can easily call it like any PyTorch model, right? Send it the image, and that's it. So here it will give you this outputs.instances, and in here you'll find lots of different values, such as predicted classes, predicted boxes. And let me see if it also has, I think we're working with MaskRCNN. If you're working with MaskRCNN, you should have predicted masks too. Let's see. Yeah, here it is. So the mask is something that is very easy to understand. As we said, it just gives you whether this pixel belongs to the object or not. So this is, remember guys, when we discussed MaskRCNN in the lecture, we said that the only addition from MaskRCNN, from FasterRCNN to MaskRCNN, is this beautiful matrix that tells you this precise pixel belongs to the object or it does not belong to the object. So basically it will help you prepare or help you do the task of instance segmentation. So for example, you come here, this is the horse. You see the bounding box of the horse is very big, right? But this segmentation is done using that mask. It's not perfect, as you can see, it's not perfect, certainly, but it's done using the mask of MaskRCNN part. So I hope now that you have like an understanding of how the output looks like. This is just the different locations. This is the X, Y coordinates of the top and top left, bottom right point. Now for the training. First, you download a certain data set and you read that data. So how does, what is he called? Detectron work? So a detectron requires the data to follow a certain pattern, and it must come in this dataset dictionaries. The dataset dictionaries is just a list of records. Each image has a record. Each record contains the following information. So the file name where the image is, the image index, the height and width of the image. So the image index is used by the data loader. And at each image or at each record, we have a list of annotations, right? Because the same image can have multiple annotations. So a record will have different objects. Each object will have the following information: bounding box, segmentation, just optional if you're working with MaskRCNN. If you're working with faster RCNN, you don't need to provide it. Category ID, if you have multiple classes, then you will have to provide the index of that class, very similarly to what we have been seeing in YOLO v4 and YOLO v5. So it's the first value in the TXT file. The box, so here, for example, we are, as we said, the X and Y coordinates for the bottom left or the top left point, and the XY coordinates for the bottom right point. And here it's just the mode. For some people, they would like to use this XY absolute. There is XY relative, and there is XYWH with height, absolute XYWH relative, depending on how you would like to represent or present your coordinates. You can just change the box mode and you will change the box information in here. After that, you register the dataset in the data catalog by registering the training and validation data and updating the classes of that dataset by just getting it. First, you get it from the data catalog and you set its classes to the list. In our case, we have just one class, which is balloon, but if we had like 5 other classes, right, so you get how this is working. Now we just sample a couple of images and we verify that our balloons are actually correctly labeled and correctly read. That is the case. We start the training. As I said, in the training, again, you take config. Either you do it locally from a file and you change it manually, but I highly encourage not to do that. Preferably do it in Python code, right? So you get the config, start the config from something that is already there, specify the training dataset from the dataset catalog. If you want to use a testing dataset or validation dataset that will, while you are training, you are also mentoring or monitoring the testing accuracy and mean average precision and all of that information, you can do that by specifying it here and it will do that by default. The number of workers, so this is for the data loader. How many workers will be loading the data, will be loading the images and applying the transformations beforehand. This is just to speed up basically the calculations. Images per batch, this is the batch size. Base learning rate, max iterations, oh, just useless stuff, right? Max iterations, similar to max epochs previously. Useless information, number of classes, how much do you have? The rest is basic code, right? So default trainer and you start the training. First, this gives you the architecture of the model. So here we see, for example, feature pyramid network. Here's the layers in the feature pyramid. Well, just a couple of convolutional layers, convolutional arrays, some ResNet, sequential convolutional layers, frozen batch normalization. Yeah, just beautiful layers that we all know and love. RPN, region proposal network, that we have seen before. So here you'll find things such as the anchors, ROI head, regions of interest heads, ROI poolers, and the fast RCNN convolutional fully connected head, right? So this is the fast RCNN part of faster RCNN, which is the same part of mask RCNN. Output layers, again, you have 2 for classification of objectness score, and you have 4 for the B-box predictions. And then you should have another few. Oh, where are they? For the classification, there should be something that ends with 1, a layer that ends with 1 for the classification. Weird. Ah, yeah, this one, it's the same one, yeah. So this one is used for 2. So basically class or background, right? Yeah, so it's 2. In case of the default one, it should have 81. So basically 80 classes plus 1. Yeah, makes sense. And then we just do the training. For example, here it just tells you information about the data. Information here, what are the things that are not loaded. So as you can imagine, the weights and bias for the classification score, for the bounding box predictor, for the ROI heads are not being used because you have 81, and in your case, you only have 2. So 1 class plus background, and here 80 class plus background. So they're not compatible, not compatible for the same reason. And yeah, that's it. So basically here you will see the training, the loss functions are going down and going up. Beautiful. Different loss functions going down and up. For some reason, it's not loaded because I think I did not run it, and I don't want to run it again because we would lose a lot of this visualizations. And yeah, after that, you just run inference and visualize it using the visualizer provided by the Dectron. And here you will come for the evaluation. This is why I didn't want to run it, because I wanted to see the evaluation. So here, AP means mean average precision for all of them. There is AP50, AP75, APS, APM, and APL. They're quite not commonly used, but let's take a look at what they are. AP50, AP75. Yeah. What does it mean? Kind of forgot these. I know M, S, and L are for well, big, small, and medium objects, but these ones I forgot. See the COCO homepage. Which confidence score is, or which range is used for AP computation? The guys from COCO confirmed there is no confidence score range. Instead, the top 100 scored detections are considered, no matter how low their confidence is. Weird. So basically, this is just, I think it's related to this, right? So the range of intersection over union used to compute the different predecisions and different recalls. But yeah, they're not pretty useful. The only one that is actually useful is the average precision, which is commonly described. This one, if you are working in a specific data set where small objects are interesting to you or large objects are more interesting to you, could be useful, but usually you will find large objects are, you get always good results on them. Medium objects, overall kind of good results over 2, but small objects, you get very bad results on it. And this is the same thing, but for the segmentation, whereas these are for object detection. So for the majority of you, this is what matters the most. This is the number that you would like to optimize. And that's it, right? This is it for mask RCNN. This is the only thing I wanted to describe. After the break, we will take a look at Supervisely. So Supervisely is a website to build, to annotate data. And yeah, here it is. So just to annotate different data sets. And it's very useful if you would like to work with different people, if you would like to collaborate, if you will have different members, different roles and stuff like that. So it's a bit more industrial. It's a bit more something that you would be able to work with in the real world, right? So we will just present that real quick. You should be able to pick it up very easily. And I will describe to you your homework once we come back from the break in like, let's say 10 minutes. No questions, right?
A quick question.
Yeah.
The segmentation thing, it always has like a separated class for background, right?
Yeah.
Okay, yeah, that's it.
Cool. No other questions? Nice. So let's take a quick break and come back in like 10 minutes for just the homework presentation. Tell me if the homework sounds too big for you guys, because for me it sounds pretty easy, but I've been working with these things for a long time, so it does not take me some time to train any of these models, because it's just like repetitive process. Just launch Colab on 3 different Gmails and you have the results in like 2 hours. And the coding part, you can do it in 5 minutes. So it should be very easy. And this is what I want from the homework to give you guys, to give you the ability to train any of these models in a very fast manner. So see you guys in 10 minutes. Hey guys, so I hope you guys are back. So now it's time for the discussion part of this lecture. So let's discuss the next homework. So for your next homework, I will give you 3 weeks basically, because there are 3 stages of the homework. The first stage is the data annotation. The second stage is the training of the different models. And the last stage will be writing a report about all of these models. So you'll be asked to train a YOLO v4 small, YOLO v4 tiny, I mean, and YOLO v5 small, and the faster RCNN architecture on the same data set that you annotate on Supervisely and you export from Supervisely. And you must write a code that converts the format of Supervisely into the YOLO v4 format, and the code that writes the or converts the the Supervisely to YOLO v5, and the Supervisely to a format that is read by the Tektron. So this is going to be your main task, you guys, and it's going to be very interesting because you will be working hands-on with these different files, all the different configs and stuff. So it's definitely going to be worth the while. It will be a little bit of too much work, so you're all welcome to use anything you find on the internet, right? So any library that you can use to, for example, convert YOLO v4 to YOLO v5 format of datasets, or any library that you find that converts from YOLO v4 version to Cocoa version. Or even better, if you find something that converts Supervisely directly to each one of these model formats, then good for you. If you don't find it, then you're going to have to write it yourself. I did write it myself for multiple times, and it's pretty short, right? So it's not something that is very complicated to write. It's just Python programming, basic Python programming, but it will take some time. So first you will create a data set, any data set that you guys would like to work on. Preferably either take some images from online that you found, or I would really like it if you just go out and take pictures. So for example, for those who go to the gym, you could just go and take pictures of some gym equipment, or like the dumbbells. For those who are like into music, you could just go around, I don't know, the new art place in Innopolis and just take pictures of some musical instruments. And I think Ahmed has a question. Yeah, go ahead.
Sorry, this happened by mistake. I'm sorry.
Nice, no worries. So yeah, for those who, it's gonna be just like an interesting opportunity for you guys to bring computer vision and object detection to your lives. So I know Utkarsh, for example, is in India, so you could just go around in India and take pictures of stuff that are Indian food, for example. And for those who are in Innopolis, or for those who are outside of Innopolis, you can go to Kazan, take some pictures of something that you find interesting, stop signs, or like those green and light thingies for traffic. Anything you guys would like to annotate, basically just take pictures, upload your pictures to Supervisely, annotate them, and train a model on that. So this will be I think it's just better for you guys to make it more customizable and personalizable, and something that you will remember hopefully for the rest of your lives. And it's definitely something that you can present to other people, and for example, to recruiters or interviews, or even to other professors, and say, oh yeah, we did a project and we did the full job from defining the task to annotating or getting the images, annotating the images, and training the models, and comparing the different models, or benchmarking these different models on our new dataset. So just the fact of having all of that experience and seeing the whole cycle being done in front of you, this is something very extra for your career, and this is definitely good for your resumes and discussions during interviews.
Can I ask a question?
Yeah, go ahead.
Should it be just one class, like one object?
Preferably 1 or 2 classes, right? So
Okay.
you're not gonna gain anything if you have like 10 classes or 20 classes, right? So there's nothing you will gain in terms of theoretical or practical knowledge. But if, for example, for you, you wanted to do that, then probably you would need lots of images. So for 10 or 2 classes, you only need like 20, 40 classes. That's max, right? For 20, 40 images, I mean, right? Preferably 50 if you want something very good. Make sense?
Yeah.
Nice. So small data set, small number of classes. Everything is just basic small models. But the goal is to basically get you through the whole process of building object detection models and to get you through the process of understanding each and every single one of these object detection models, how to train them, all of that, right? Does that make sense?
Can I ask a question?
Yeah, go ahead, of course.
Yeah, did I understand correctly? So I do like 100 photos of 2 objects.
Yeah.
And then I use some pre-trained YOLO V4
Yeah.
to detect those objects and make some kind of a report.
Yep.
And do I have to do multiple models or just one YOLO V4 will be enough?
1 for YOLO V4 small or YOLO V4 tiny, 1 for YOLO V5S, and 1 for YOLO or for Detectron. Basically, faster RCNN.
Models that we have to benchmark.
Can you repeat?
Will we have a list of those models? Like so.
Yeah, of course. Yeah, of course. I will give you like a document that describes the project in detail.
Oh, okay. And that's our second assignment, right?
Yeah, it's a second and third assignment. So it's just basically the final assignment of the course, and it will have the grade of 2 assignments.
Oh, okay. Okay, thank you.
Cool. Do you guys want to work in pairs, maybe, or simplify the job for you?
I think it's
Yeah, I
good.
think it will be a good idea. Why not?
Okay, so for those who would like to work alone, I would be more forgiving. For those who work in pairs, I will destroy you. No, I mean, just have higher expectation. No worries.
No, you will destroy us.
Yes.
So it seems too many people will work alone.
No, no worries. Like I would just expect better code, right? So for somebody who is going to write a report alone, just anything is good. For those who are working together, I would like to have very detailed reports, right? So just something that says this one did the work and that one did the work, right? So it's definitely going to make things easier for you guys because you're not going to have to do the annotation twice and stuff like that. So it's much faster. But yeah, it's going to be fun. So anybody has some ideas or some clues for objects that they would like to annotate?
Maybe like these rovers, Yandex rovers.
Good. I think those small things that are doing the delivery also from Yandex.
Yeah, these that's what I'm saying. These small robots. Now they have basically actually 2 classes of them. They have a new model, so
Okay.
they are now 2 classes. So maybe you can just take 50 photos of them. They're like always around.
Yeah, just follow it and just like keep taking pictures in different scenarios, different situations, and
Yeah,
that's it.
exactly. So
Nice. Anyone else has a different idea?
I'm gonna take a photo of my cat.
Awesome. Really good idea.
I have a lot of photos in my gallery.
Okay. Yeah, that's true. That's a good one. Anyone else? Good idea, Utkarsh. Yeah. Anyone else? Maybe something that you guys are working on already, or something that or field that you guys are interested in. Some people are doing maybe karate or judo or I don't know, yoga. dancing, music. You can apply it to anything you guys want. Even if you want, like you can apply it to the chairs of Innopolis. Like you just go to Innopolis lecture rooms and just take pictures of chairs, take pictures of students, professors, anything you want. Of course, ask for permission. Nice. So this is it for the homework. I will give you guys later a much more detailed description of the task and the steps to make. And that's it. Now, do you guys have any questions about the course in general or about today's content specifically?
I guess we will have questions when we start working on the assignment.
Yeah, you're always welcome to ask me any questions. Of course, you're already used to sending me messages, and you can ask, of course, your friends also in the chat. Feel free. And as I said, anything that is online, any library that exists, any piece of code that is online, always leverage it. Never rewrite something from scratch. So I guess if you don't have any questions, we could move to the next step, which is individual video calls, right? No questions? So just to give you guys the list of the students who asked for a meeting, I think Maxim Ilgarov, we already discussed this. Are you here? Yeah, so you're first. And then we have Lev. Then we have Anya, then Hussein, and then Utkarsh. Anybody else wants to have like a one-on-one discussion about their projects?
I won't. Maybe after Utkarsh.
Yeah, after Utkarsh, I will text you. Then just send me a message, just so I don't forget.
Okay.
Right now? Yep. Anybody else who also wants to have like a one-on-one discussion about your projects, just send me a message right now, and we will have. I will just like text you back and send you a link for just a Zoom discussion, right? Sure. So thanks a lot, guys, and I'm gonna send Maxime another link basically to join another Zoom meeting, and we will discuss there. And once we finish, I'm gonna send the next person and the next and the next. That's it. So thanks a lot. Have a great weekend, and go out and take pictures.
Thank you.
Thank you.
Goodbye.
Bye bye.
Have a nice weekend.
Thanks. You too.